We saw if your h of n and x of n are finite, then it is very simple. Now what happens if your h of n or x of n, any one or both, are infinite? Then what? And the example here actually shows that if, let's say, both of them are having infinite number of impulses. Here we see that our h of n, this is our impulse response, is equal to your u of n, which is a step signal which becomes 1 at n equal to 0 and remains 1 throughout. So throughout it just remains equal to 1 and it goes all the way to infinity. Then what? So this becomes very, so you can say, involved in that sense. I was saying that if we have this h of n, which is infinite set of impulses, and if your x of n also is infinite, so these are pulses which goes on and on and on and never really becomes zero, so they are going all the way to infinity, here also and here also. If these are your infinite set, and specifically this alpha raised to power of n un, I talked about it in the introductory lectures also. This is not exponential decay. This is basically very similar to that exponential decay signal, and you will come across this signal a lot. So let's take any questions.
Sir, can you add Abdul Wahab?
Can you what?
In the lecture, he is unable to get invited.
So how should I invite him? I should just type a name of Abdul Wahab or what?
Yes, so there's a section for participants.
Okay, Abdul Wahab. He's from 40. Is the one? So I think he's in. Okay. So Wahab, can you hear me? Wahab, can you hear me?
Yes, sir.
Okay, thank you. So we were actually seeing what a raised to power of n un signal actually is, and I will just quickly go over this signal. I believe to some extent I referred to this earlier also. So some constant raised to power of n un. Now what is this un multiplied to something, and what is a of n itself? Let me talk about this. So if we just talk about a of n, this a, the possibility can be, this a can be less than 1, a decimal value. It can be equal to 1, or it can be greater than 1. You will see mostly we are interested in a less than 1, or typically magnitude a less than 1. Most commonly you will just come across the value a less than 1, positive values, decimal values. This is of point of interest, and this type of signal a and un where a is less than 1, you will come across this signal a lot in future courses throughout your engineering career. So this a and un, you should be comfortable with what this signal is. If we take any value of a, let's assume that, just as an example, a is, let's say, 0.5, then this is your n axis, then n equal to 0, anything raised to power of 0 is 1, it will always start from 1, and then n equal to 1, it becomes 0.5, then it becomes 0.25, then it becomes 0.125, then 0.0625, and then it goes on and on and on, but it never really becomes 0, it will just go on and on and on. So it will be a decaying sort of a signal. So this is a very common signal, and if you go on the negative side, if this un was not there, then you will have values on this negative side also. On this side you will see that it will just keep increasing. It will be value equal to 2, I believe, and then 4 and all that. It will just keep going on like that. So it will be just sort of a signal going like this if it is just an. But if you multiply un to it, we know that un is a step signal. Un is a step signal which is 1 throughout. The effect of multiplication of un is basically the whole signal gets multiplied by this type of a thing, and you see on this negative side it is all 0. So this type of thing you will come across. If we just multiply this any signal with un, the effect of multiplication of un is that the negative side gets cancelled out, and you are left with only this whole side gets cancelled out. You are left with only this signal. So right hand sided signal. This un has the effect of making the signal right hand sided. So a and un is basically a decaying sort of signal which will start from n equal to 0 and go on and never really becomes 0. It's a decaying signal. Now if this a is equal to 1, then the whole signal, anything raised to power 1 is still 1. Your a and un ends up becoming this signal. A and un ends up becoming same as un. So just once throughout, so never changes. It's a constant signal. Here we have decay, here we have a constant signal. And the third situation would be where a is greater than 1. If a is greater than 1, let's take an example, let's say 2. So any power of this a which is greater than 1, you will see that as we keep increasing the power, its value keeps increasing. So if we take, let's say 2, it will interestingly also, all of these will always start with 1 because anything raised to power of 0 is 1. And here it will become 2, then it becomes 4, then it becomes 16, and it just keeps increasing or growing throughout. So exponentially increasing or growing signal. So a and un, normally this signal we are not interested. This again same as un. Mostly you will be coming across a signal like this, a and un, where a is less than 1. So be comfortable with this signal, and this decay that you see, if you compare it with your exponential decay, the difference will be that this rate of decay is kind of different. Otherwise also it's very similar to just keep becoming smaller, 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 but never really becomes 0. So this is your a and un, and be comfortable with this signal. And this is what you see right here also. Here we are given that your x of n is alpha raised to power of n, where alpha is a constant, a decimal value between 0 and 1. So in that case, as we saw, it will be this decaying signal. Alpha raised to power of 0 will be 1, and depending on value of alpha, then alpha raised to power 1 will be alpha itself, and then higher powers. However, higher powers of decimal values are always smaller values. We already know that from maths. So we have these two signals, and both of these signals, if you see your impulse response h of n and your x of n, this actually, both of them have got infinite number of impulses, or sort infinite sort of a representation is here. So if you have this situation, then how do we find out the result? And I said that here it is directly written that yn is summation this. Now we know that y of n, if you are given x of n and h of n, it is basically convolution. X of n convolve with h of n. And what is convolution? We know that convolution is convolution sum. K equal to minus infinity to infinity, x of k, h of n minus k. This we already know. Now, if we just see this example where we are given h of n and where we are given x of n, but both of them are infinite values. And then from here, how do we get there? Once we plug in values, how do we end up getting here? This is something which I think in the last lecture I said just go through it, and it will be very interesting to see that how this happens. So did anybody go through it? So how do we reach here? Anybody? Any volunteer who can just shed light on this? We have x of n, which is alpha raised to power of n un. And we have h of n, which is simply un, and then we have to find y of n, which actually is summation k equal to minus infinity to infinity x of k, h of n minus k. Right? If we plug in the values, end result we know we are going to reach there, but how? So k, now let's just put in the values first. So x of k is alpha raised to power of k, u of k, and h of n minus k would be u of n minus k, because h of n is u of n, h of n minus k will be this. So this is your y of n. If you remember, directly we are given in the slide that your y of n is basically summation k is equal to 0 to n alpha raised to power of k. So how do we reach from here to here? Any ideas? Okay, so that means many of you, or rather all of you, didn't really pay much attention to this. Now here comes a very important point and a very important, you can say, technique, which in mathematics you may have or may not have seen. With experience, I know people don't really cover it in mathematics, but let me cover here. So this is basically a summation, and inside summation we have this u of k, u of n minus k. Now we know this k is basically our axis now, because you see summation is for k and this is your k axis. Like we have this n, we have u of n with n axis. So instead of n, if we call it k, it's one the same thing. So u of k, if we just plot u of k, it's also a step signal, same thing, all ones starting from n equal to 0 and going on and on and on and on and on. So this is your u of k. Starting from 0, the value is 1 and it remains there for all values of k all the way to infinity, which are positive values. This is u of k. And let's talk about u of n minus k. So if we have u of k, then if we flip the axis, then u of minus k would be the flipped version. The axis gets flipped. So k gets replaced by minus k, and you see that it is all ones going all the way to infinity. So these are for negative values of k. This is k, and this is your negative values of k, minus 1, minus 2, and like that goes on and on. So this is your flipped version, your u of minus k. Now u of n minus k. Now we know that if this was k axis, so k minus something, let's say k minus 1 will be this thing shifted right by 1, and k minus 2 will be this thing shifted right by 2. K plus 1 will be shifted left by 1. K plus 2 will be shifted left by 2 units. But if we do the same here, instead of this k minus 1, if we have minus k minus 1, then you will see that the effect is opposite. Effect would be sort of opposite. Instead of that shifting right, it will be shifting left. So this n minus k, you will see this effect would be, we are adding minus k plus n, or n minus k is one the same thing. So if we add something, like we add plus here, it is basically typically shift left. But if it is minus k, you add something, it will be opposite because the axis has been shifted. So you can just think of it as we just add something here and then we flip the whole thing. So u of minus k plus n would be this whole thing shifted not left but shifted right by n units. It will be shifted right by n units. So this is your 1. So this will be your u of minus k plus n, or we can call it as u of n minus k. So whatever way you want to write it. Typically we also write it as u of minus k within bracket is minus 1, minus k minus 1 within bracket. We can write it like that also. So u of n minus k, typically it is very easy to remember rule of thumb. U of k or u of n, we just subtract something from here, that means shift right, or delayed shifting right. We add something, it is shift left. But if we have u of minus k or minus n, you add something, it will be shift right. You subtract something, it will be shift left. So this is the thing that we need to remember. So this was just describing what is u of k, u of n minus k. Now, what effect does this has? It sounds very intimidating that inside summation we have all this some constant raised to power of k, u of k, u of n minus k. But remember, whenever inside your summation you have this step signal, both of them are step signal. It is a simple common step signal, and this one is flipped and shifted step signal. So this one is flipped and then shifted step signal. This is also step signal. So the property of step signal is that for a range of values of this subscript, here we have k, for range of values of k, this step signal will be 1, and for certain range it will be 0. Like here u of k, for k equal to, this will be equal to, let's say 1 for a certain range of k, for k greater than equal to 0, and for certain range it will be 0. It is 0 for k less than 0. Similarly, u of minus k, this is also step signal but flipped. For certain range this value will be equal to 1. It is 1 for k less than and equal to 0, and this is equal to 0 for k greater than 0. Similarly, this is also steps. So any shifted flipped step signal has got this property that for certain range it is 0 and for certain range it is 1. Certain range is 0, certain range 1. Same will be true right here. For certain range of k, this value will be 0, and for certain range it will be 1. So the effect of step signal, whatever version of step signal you have, whether it is, if you see u of something, it is a step signal. So if it is just u of n or u of k, it is just common simple step signal like this. If you have something like this, it is basically flipped first and then shifted, flipped and then shifted. And if you flip and then shift, then the property of shift also get inverted. Now addition will then mean shift right, and subtraction will mean shift left. Here addition will mean shift left and subtraction will mean shift right. So these few things we have to know, but one thing we know that both of them are step signal. So if you have this step signal u of anything inside a summation, the only effect this step signal has is it will just change your limits. It will just change your limits. Why do we say change your limits? Let's take them one by one. Let's take this one first. If we see the summation for k, we can divide the summation into two parts. For k minus infinity till just under 0, from minus infinity to minus 1, this value will be 0, and then for k 0 to infinity, this value will be 1. So the first part will become 0, the second part k equal to 0 to infinity, this alpha k, this step signal is 1. For second part from minus infinity to 1, that part is 0, so we can just skip that. So the effect of this uk, if we just see, is basically just changing the limits. It just changed the limits from minus infinity to infinity, it gets changed to 0 to infinity. Because from 0 to infinity, this value of the step signal is 1. And then we take this second step signal. If you see this second step signal, now in summation, now range of k available to us is from 0 to infinity. From 0 to infinity, this is your u of n minus k. So from 0 all the way to infinity, this is the range available. We see that from 0 to n, its value is 1, and from n plus 1 to infinity, its value is 0. So we just take 0 to n, the first part, where this one is 1, and then from n plus 1 to infinity, this value is 0. So multiplication factor, if it becomes 0, the whole thing becomes 0. Just like we saw for this one, for minus infinity to 0, this part was 0. That's why we just considered the second part. So ultimately we end up getting this thing that we were trying to go for right here. So this is what you get, your y of n. So your y of n ends up becoming summation k is equal to 0 to n alpha raised to power of k. Anybody having any confusions here? So this is a very interesting example, and the technique that you must you can say master starting from now is that if you see any summation in which we have this step signal multiplied, then we can just know that this effect of step signal will not be to change your values of this summation. It will be just changing the limits. If you have more than one step signal, then we take the step signals one by one. Now it's our choice. We can take either one first. We could have taken this one first. For example, if we had taken this one first from this summation, this signal is signal right here. Now this step signal would be 1 all the way from minus infinity to n, and from n plus 1 onwards it would be 0. So in that case we would have written it like summation k equal to minus infinity to n alpha k u of k into 1. And from n plus 1 to infinity, this part was 0, so we will not consider that. So that is taking this one first. And then we take the second one, and the second one is here. Now the range available to us is from minus infinity to n. From minus infinity to n, again, the signal u of this k is 0 from minus infinity to 0, but from 0 to n it is 1. So we just take from k equal to 0 to n alpha raised to power of k, the signal is 1, because the other part is 0, we are just not showing that. So whatever step signal you take first, it's your choice, but if you have step signal inside summation, it will always have the effect of changing the limits. So here we see limits are not defined from minus infinity to infinity, we have two step signals. This step signal has property that it is having value 1 within a certain range of k and 0 within some other range of k. So we just take the range of k where this value is 1, because the other range doesn't matter, it will be just this thing plus for the other range it will be just 0. It will be summation something which will be 0. So the range with which this is 1 is from 0 to infinity, from 0 to infinity. So we take this where it is 1, and then we take the next step. In next step signal, again we say for what range this is 1. This is your step signal. It is 1 from minus infinity to n, but limit available to us for k is from 0 to infinity. So in this 0 to infinity, the first part from 0 to n, this part is 1, and from n plus 1 to infinity it is 0. Either we could write this summation like that and then put it equal to 0, but there is no point even writing it, so that's why I don't really even write it. So ultimately we end up getting this, which was our original thing right here. So be comfortable with this small, you can say, information, and this will become very useful later on once you solve different sort of you can say questions and scenarios in this course also, in DSP also, and then later on your real life also. Any questions, any confusions here? So if there are no questions, let me go back to the slide. So in this example, assuming that all of you are already experts in mathematics, they have just shown h of n is that x of n, that just plotted your x of n, which was this sort of a signal, plotted h of n, which was your un step signal, and then assuming that you already know that y of n is convolution, it is convolution sum, and you know that this step signal, the effect would be changing the limits, you end up getting k equal to 0 to n alpha raised to power of k. So lots of assumption available right here. But I hope by now you should be comfortable in knowing that how we actually reached from all these steps all the way to here, just by plugging values for this h of n and x of n. So this is summation k equal to 0 to n alpha raised to power of k. Now comes another thing, that how do we reach from here to here, and then how do we reach from here to here, and specifically why do we get this u of n right there. Let me continue from that thing onward. First of all, let's just refresh a bit of your FSC and maybe the previous mathematics you have done. You may have seen this a raised to power of n summed for n equal to 0 to infinity. Does anybody remember that? What was this equal to for a less than 1? What was this equal to? To be very specific, let's call this. Does anybody remember this formula from FSC? Guys, high flyer in mathematics. What is this summation? This is a series. A raised to power of n for n equal to 0 to infinity. What is this sum of series? Nobody remembers it? You remember this formula? So this is what you saw in your FSC in mathematics, that if you have a raised to power of n sum for n equal to 0 to infinity, if you open this up, it is something like that: a raised to power of 0 plus a raised to power of 1 plus a raised to power of 2, all the way, it goes on all the way to infinity. So this value we can write it as sum of n is equal to 0 to infinity a raised to power of n, and from FSC we know that this is equal to 1 over 1 minus a if your a is a decimal value. It is less than 1 or decimal value. Then it is just equal to this. So this is one formula that we saw in mathematics, and we'll be using it a lot in solving convolutions, especially for infinite sort of a signals, and we will see how it actually helps us. Okay, so the other thing that we need to see is if instead of 0 to infinity we have this n is equal to 0 to some capital value n, then what happens?
So you asked if we have this summation series, then what will be the outcome?
Yes.
So the
What
summation will stop at a power capital N.
and the denominator part that remains the same.
Yes.
Okay. So this is what we have, and you will see that this is what we are going to get. So this is the summation for n equal to 0 to some limit. So using these two formulas, you will see we'll be able to solve convolution for infinite type of signals. Invariably, you'll end up using either one or the other formula, but remember that these formulas are valid only if you have a, which is a decimal value, or a, you can say, a decaying sort of a situation. So we can sum up this thing if a is a decimal, because higher powers of decimal become small, small, small. We have a decaying sort of a thing. So this is, let's say, your signal n a raised to power of n. And because it is starting from 0 onwards, so at times we can just write it as a n u n. Otherwise, if you don't write it as a n u n, we have to actually specify that it is for value of n from 0 to n. So if you just write a n, that means your signal has values on this side also. But if you just multiply un with it, that means your signal starts from 0 and goes all the way to infinity. So this un actually makes sure that we have values valid only for the right hand side. You will see that this type of summation will be very useful for us. Now let's come back to our question again and see that where we were. So this summation, we know that it is limits not from 0 to infinity, it's from 0 to n, k equal to 0 to n. So if we just plug in the formula, it becomes 1 minus alpha and 1 minus alpha raised to power of n plus 1. So this is your y of n. But interestingly, the other question asked was that why we ended up getting u of n right here. Now the effect of multiplication of u of n is that we ensure that the values of n would be valid only from 0 to infinity. That is the only effect of this u of n. Now if we don't write u of n with this, that means we can have plus or minus values of n. Now if you remember, in the summation you had two step signals, u of n minus k, and once we plugged in the limits, because of this first one, the limit was from k equal to 0 to infinity alpha k, and because of the second one, the limit became summation k equal to 0 to n alpha raised to power of k alpha raised to power of k into 1. So this second part, if you remember that second signal, it is basically this step signal flipped and then shifted. If I just try to draw it here, this was your u of n minus k on the k axis, and for this signal, this n was a constant number and this was number of shift. This was your n. If n was a positive number, it would have been shift right. If n was a negative number, it would have been shift left. If n was a negative number, then if n was a negative number, then the whole thing would have ended up giving us 0. So that means we cannot have negative values for n. If n is a positive number, then yes.
सर स्लाइड बिल्कुल ब्लैंक नजर आ रही है, आप कुछ लिख रहे हैं तो वो नजर नहीं आ रहा.
Okay, let me see. You are seeing example 3. So this Can you see this writing right now?
नो सर, बिल्कुल ब्लैंक है, वाइट है.
Okay, so this was what we saw, that if you have this u of n minus k, then this n is basically the number right here. So n will be a positive number. Now because of this, if we see, just to ensure that n is positive, it cannot be negative, we write u of n. That actually ensures that y of n will be valid for positive values of n. This u of n actually ensures this. So this was the complete example. Any questions here? So this is what we wanted to cover right here. And I'm sorry, I will just stop the lecture right here and we will continue next time. If you have any questions, please quickly ask.